In the last video, we talked about one-dimensional motion. But if you want to win the battleship competition, we need to understand motion in 2D. It's actually not as hard as it sounds, and there's an easy trick. Only focus on one dimension at a time. If you do that, it's about the same as what we did before. When we calculate the trajectory of a projectile, we make a few assumptions. Number one, gravity is negative 9.8 meters per second squared in terms of acceleration. Number two, there is no acceleration in the x direction. There's no gravity in the x direction, and we will ignore wind resistance and friction for the sake of simplicity. Number three, and this is a big one, the projectile begins and ends at the same height. This isn't always true in the real world, but for the sake of simplicity in this class, we'll focus on situations where this is the case. Picture a tennis ball flying across the tennis court. As it moves through the air, it creates a parabolic shape, like a parabola. But if we focus only on the y direction, we'll see that its motion is exactly the same as a tennis ball that's thrown straight up into the air. It starts at an initial velocity and travels straight up until the velocity is 0 at the top of its motion, and then gravity pulls it back down. It has a negative velocity when it reaches the ground. In the x direction, it travels at constant velocity until it lands. In the real world, we have things like air resistance and friction, and calculating with those things in mind just gets calculus-y, and we just won't go there. So if we want to figure out how far our projectile goes, or can go, then we need to evaluate the x dimension and the y dimension separately to solve for some similar information. Okay, here's where it gets a little messy. We need to talk about angles. When we fire a projectile, most of the time it's not shot straight up or straight over. It's shot at an angle. For projectiles, most of your projectile angles are going to be between 0 and 90 degrees. At 0 degrees, the motion is all in the x direction. There's no y direction. At 90 degrees, all of the motion is in the y direction. There's no x component. If we pick an angle in between, there's going to be a combination of x velocity and y velocity, and we use trigonometry to figure out what those components are. Since we're splitting x and y dimensions to make things simpler, we need to know the x component and the y component of the velocity, and we can use a simple equation to do that for each dimension. For the x dimension, the velocity component is Vx is equal to the original velocity times the cosine of the angle, or the cosine of theta. For the y dimension, the equation is very similar. It would be Vy is equal to the original velocity times the sine of theta. So if we have an object that starts at 35 meters per second and it's fired at a 35-degree angle, the y velocity would be about 20 meters per second, and the x velocity would be about 26 meters per second. Because it's at such a shallow angle, most of the velocity is in the x direction. Here's the neat part of this calculation. For the x and the y direction, there is one thing that's the same for both: the air time. Both the y dimension and the x dimension take the same amount of time from start to finish. Since we know the acceleration of gravity, we can use that to find the time using the y dimension information. What we need to know is how long it takes for our projectile to get to the top of its motion. It will take the same amount of time to get from there back to the ground. So if we think of that as half of the time, then we can solve for that information using the basic definition of acceleration, a equals delta v over t. If we solve for time and double that number, we know how long the projectile is in the air for any example. And if we plug in our equation for the y component, then we get a general equation for time in the y direction. T equals 2 times the initial velocity times the sine of theta, all divided by g. Once we know the time, we can plug it into the x component to solve for x, or how far it goes. We can also just put those two equations together to get one simple equation that we can use repeatedly. Well, it's not so simple. So our range equation to figure out how far a projectile goes is x is equal to 2 v naught squared sine theta times cosine theta divided by g. It's a little messy, but it's easy to plug into if we know all that information. Let's look at some example problems. Suppose a cannonball is shot at 52 meters per second at an angle of 41 degrees. What is the range of the projectile? Since we are solving for x, we don't need to rearrange this, and we can just plug in to solve, and we get a range of 273 meters. Let's look at another example. This time, the velocity is 48 meters per second of the cannonball, and the range is calculated to be 220 meters. What is the angle? First, we need to rearrange to get theta by itself. Multiplying both sides by g gets rid of that on our side, and we divide both sides by vi squared. But the theta is still inside the sign. To move the sign, we use the inverse sine function on both sides. This cancels the sign, and our final equation is theta is equal to 1/2 of the inverse sine of gx divided by v naught squared. Plugging in our numbers, we get 34.7 degrees as our answer. We will look at more examples in class tomorrow. Be sure to go back and take notes on this video if this problem was confusing.